Okay, welcome. Happy Thursday. All right, so fine, I'll say it. Quiz number 3 this weekend. So starting tomorrow, of course. So today we're going to wrap up chi-squared tests. And I kind of gave you a preview, a sneak preview last day that, okay, we're going to start with just looking at one variable, one categorical variable. But what if we have 2 categorical variables that we want to compare? Then that's what we're doing today. Okay? But nothing really changes, but it's a little bit different from what we've seen in the past. So let's just do a little bit of review. We did chi-squared tests, for goodness of fit. And so what we said was, okay, for chi-squared tests, we're only going to do hypothesis tests. Okay, and so we only do hypothesis tests. And I'm sure there are confidence intervals out there, but because you've got multiple categories, you'd have to build confidence intervals presumably around each of them, and you might have to make adjustments for doing multiples. And so I'm not too familiar with that because most of my work is in quantitative data, so numerical data. But for us, we're definitely only going to do hypothesis tests for chi-squareds. For chi-squared questions. So last day, goodness of fit, we used the goodness of fit test, and it sounds weird, right? But we have some idea of what the population might look like. And then we want to compare, okay, does our sample, does that kind of match what we're seeing in our population and what we would expect, right? And then it all hinges on that expectation. What do I expect to see here? Okay, and so we only do hypothesis tests for chi-squared test questions, and goodness of fit tests. Goodness of fit is, 4. I don't know where the E came from, is for comparing more than 2 categories of one categorical variable, or comparing counts in more than 2 categories. Right, for one categorical variable. For one categorical variable. Someone's like blasting the music out there. It's weird. And it makes me so curious. Like, what's going on out there? Okay, so a goodness of fit test is for one categorical variable. Okay, and so usually we have a table like this, and this is what we call a one-way table, right? And so I've got category 1, category 2, category 3, and maybe category 4, for example, right? And then I have the observed count in each category, right? Okay, so this, maybe I should use a green, different color. This is what we call a one-way table, right? Because it only has one categorical variables. We're only concerned with one variable here, but it has multiple categories. And then we want to see, okay, do these categories, do they fit the distribution that we suspect that it should, right? Or do we have evidence that the observed counts are significantly different from the expected counts, right? And so that's where we got to last day, or what we did last day. We spent some time figuring out, and intuitively we know how to find these expected counts, right? We would say, okay, well, for example, if I'm expecting an even spread here, right, I would expect the probability of being in each category to be 1/4, right? The number of categories, right? And so we use that and multiply it by the total, and then that gets us the distribution, right? The hypothesized distribution, or the null distribution, right? And so our null hypothesis can be a little bit tricky because we're no longer using Greek letters and symbols, which once you kind of get used to that, then I find that they're quite easy, because you just remember what you do and then plot them down. And a little bit trickier for chi-squareds is because we're going to be writing out the null hypothesis. There's really no easy way to show the null hypothesis in symbols, right? So the null hypothesis is that the distribution, so the observed distribution of counts, follows approximately the same distribution as the expected counts. Now, there's lots of different ways that you can phrase this, right? And so depending on the question, right, I think we had a question, what was the question before that we had? Oh, the jury representation, right? And so we said, okay, the distribution of race in the jury, right, is representative of the registered voters, right, or the proportion of the races in the registered voters. So it depends on the question, and that's what's really tricky, right? And so you'll need to practice that. On the quiz, I'm not going to make you write it out. It'll be a multiple choice situation, right? And so so that'll be better, right? Whereas maybe on the final, I'm kind of tempted to make you write it out, but there's a lot going on. So maybe I'll just save that for when I teach it another time. Make them work harder, right? But you should be able to write it out on your own. All right. So the null hypothesis is that the observed counts are not significantly different from the expected counts. Right? So, or some take on the goodness of fit. Oops, is really the distribution, right, of our observed distribution fits the expected distribution. Good. Right? The observed distribution fits the expected distribution. Good. That's not proper English, right? But I'm just mapping it back to the goodness of fit, right? So fits the distribution, good. So you can use that to kind of help you remember, right? It's a goodness of fit test if you have one variable, right? And then of course, the alternative is going to be the reverse of this, right? So the observed counts are significantly different from the expected counts. So usually I don't even really spend too much time on the alternative. I just reverse it. So the observed counts, I totally could have copied and just crossed out. There's still time, I guess. Are significantly, I won't do it because I know you're writing too, are significantly different from the expected counts, right? That's tricky. So depending on the distribution that we want to see if our observed distribution fits that expected distribution, right, then we'll be able to find expected counts, right? And then we said, okay, well, the distance between these two, once we take into account the spread, which turns out it's the square root of the expected count, which we kind of glossed over to be able to cover the material because we don't really need it so much, right? But then we said, okay, the chi-squared test statistic. And the reason I'm reviewing this so much is because we're going to use the chi-squared test statistic again, right? And so it's going to be really important to keep track of which one, but how we calculate the test statistic is the same, right? And so you have the observed counts, observed minus the expected counts squared divided by the expected count. And then you have to add these all up. Right? So each cell, right, has an observed count and an expected count. So then you take the observed minus the expected, you find that distance, and then you square it, right? That amplifies larger distances, right? And then divide by the expected because that's translating to the spread. And then we can add all those up. And then that's your chi-squared test statistic. And then we said, okay, we're going to use chi-squared, a chi-squared table, or you can use software. But I would probably just use the table. But to use the table, oops. To use the chi-squared table, we need the degrees of freedom. For a one-way table, right? So for one categorical variable, then we just have the number of categories and that's it. So then it's the number of categories minus 1. Right, so for a one-way table, the degrees of freedom is C minus 1, the number of columns minus 1. C is the number of categories or columns. Okay. Whereas, right, we're going to introduce a two-way table where we now have two categories and we want to see if they're independent of each other, right? And so it's things change a little bit, but not really, right? How we tackle the problem stays the same. So that's really nice. But then we have to take the number of rows into account as well, right, for our degrees of freedom. But then once we have our degrees of freedom and our chi-squared, we're off to the races, right? We can use the chi-squared table and you can either find the p-value or you can use the critical value approach. Of course, the question's going to guide you, right? It'll ask for the p-value or the critical value, right? And so we need to be prepared to solve it both ways. Now, we have just focused on the p-value approach, right, so far for our hypothesis testing questions, but we could have used the critical value but because we have the Z table, it's just easier to use a p-value approach. Okay. Right. Our conclusion can come from one, the critical value, right? Where we said, okay, given some alpha level and our degrees of freedom, right? Let's go back to the table here. Given some alpha level, and remember, chi-squared is only on the one side because it's this kind of skewed distribution. And depending on how many categories you have, it's going to kind of start to slowly mosey over and become slightly more normal, but not quite. And so even with 7 degrees of freedom, right, you've only got this quick slope here, and then it's still quite skewed. So it'll always be skewed, and it'll be skewed to the right. So our p-value is always going to be the area in the upper tail. Okay, so what we said was, okay, if I want to use the critical value approach, then I need to decide what my alpha level is up here, typically 0.05, right? And then depending on the degrees of freedom that I have, and of course it increases, can you imagine having 51 categories? That's unlikely, right? But we can handle that with this table. But usually most of our degrees of freedom are kind of less than 10, right? So you can kind of focus on this section of the table. And so once you have your degrees of freedom, the number of categories doesn't change, right? So then you're stuck on that row of the degrees of freedom. So if you have, let's say 2 degrees of freedom and an alpha level of 0.05, your critical value would be 5.99. So how we use that critical value is we say, okay, I have forced, let's say maybe this one, I've forced this area, the p-value, to be 0.05, right? What value of chi-squared is going to make that happen? And then is my value of chi-squared beyond that, right? Because that means that my p-value would be less than 0.05, right? And so that's the critical value approach. And so the critical value, if our calculated chi-squared is larger than the critical value chi-squared, and maybe I'll put a little subscript crit usually. So if the chi-squared that we've calculated is larger than the critical value, we have enough evidence. We have enough evidence to reject H0 in favor of HA, right? Or staying on, so the other option is the p-value approach. So using our degrees of freedom, right? You stay on that line and then you try to place where your calculated chi-squared would go, right? And so following the appropriate degrees of freedom line in the table, we place the calculated chi-squared, test statistic, if you want to call it that, the calculated chi-squared where it belongs on the number line. Where it belongs on the number line, right? Because those chi-squareds, as the area in the tail is decreasing, those chi-squareds are all moving out further into the tail, right? So you can place your chi-squared on the number line and find the corresponding p-values. And find the corresponding p-values, which are the upper tail areas. I think they're called that in the, right, yeah. So the upper tail, these are p-values. To find the corresponding p-values that wrap around our calculated chi-squared. Notice how I'm really distinguishing between the calculated chi-squared and the critical value, right? Because they're both chi-squareds, but one is the one that we're actually working with. One is coming from our sample, and that's the one that we want to be working with, right? And then the critical value is just a value that we can compare it to, right? And then our conclusion here, of course, stays the same. If the range of the p-values is less than 0.05, right? So if the range of the p-values is less than 0.05 or less than the alpha level, we have enough evidence to reject H0. We have enough evidence to reject H0, right? One of the things that people kind of get bogged down in is, well, what if the alpha level is inside the interval? Well, that's very hard for that to happen, right? So if it's, let me see here. Let me just copy this in so I can draw on it. So let's say, for example, that I have 2 degrees of freedom. And I'm going to let this be my alpha. I'm going to let 0.05. Let alpha be 0.05, right? And then let degrees of freedom be 2. How many categories do I have then? That means I have 3 categories, right? Which is a reasonable thing, right? So this is just to show you what happens. Okay, so if my calculated value is somewhere near 0.05, well, it's either between 4.61 and 5.99, which means my alpha level is somewhere between 0.05 and 0.01, right? And so my 2 options here, right here, so let's say my calculator is somewhere, so my chi-squared calculated is somewhere here, then my p-value is going to be between 0.05 and 0.1. Okay. I can still see, unless my chi-squared is exactly 5.99, which is never going to happen, right? It's either going to be on one side or the other. So here I can tell that this whole interval is above 0.05. Okay, so this interval, oh, I can't write today. Oh, can't even fix my writing today. This interval is above alpha equal to 0.05. So you don't have enough evidence to reject H0, right? Whereas let's say your calculated chi-squared is somewhere here. Oops. So now your p-value would be between 0.02 and 0.05. If my alpha level is 0.05, then, well, if it's somewhere between 0.02 and 0.05, that's less than 0.05, right? And so this interval is below 0.05. So even if you're on the cusp, you can still find your answer, right? And so this interval, it's just hard to make the change between a hard number, right, that we're used to from our Z-scores, and going to an interval, which is a little bit more flexible, right? There is some p-value that we could find using software, but we're also just as powerful with just the interval, right? And so this interval is below alpha equal 0.05, right? So it's less than the alpha level, which means you have enough evidence to reject H0. Okay. I'll call that the end of our review, right? Kind of a long review today, but it's worth it because we're gonna just go through it all again, but with two variables. But the one thing that I forgot to mention, or really didn't have time to mention last day, was the assumptions for chi-squared. Okay, and so the assumptions for conducting a chi-squared test. Remember, we're used to these huge assumptions, and this is why it kind of slipped my mind, is because these assumptions are like breezy in comparison, right? We're used to checking, okay, do I have a random sample? Is the sample size less than 10% of my population? Do I have 10 expected successes and 10 expected failures, or 10 observed successes and 10 observed failures, right? We're used to going through, and if I have 2 samples, I have to check it for both samples, right? So we're used to having these huge assumptions. But for a chi-squared test, what's nice is there's 2 assumptions, and there's really only one that's gonna be a bit of a problem. So the assumptions are that the counts are independent of each other, right? And so the counts, there's really no overlap in the counts. You're either in a category or you're not, right? You can't be in 2 categories, for example. And so the counts are independent across the categories. The second one, and this is the one that's kind of a little bit strange in the beginning, is we have to have at least 5 expected counts in each cell, right? And so where is it, the observed? Well, now I'm second guessing myself. That's never good, right? Let's see here. They talk about it. I know they do. I know they do. Okay. Expected cases. In fact, maybe I'll just sneak this. Why not? But it is exactly what I said. All right. And so each particular scenario so each cell must have at least 5 expected counts. So the expected count for each category must be at least 5. Okay. So you can't have a probability that's so small that you're only expecting to see 2 successes, because that's going to get lost in the shuffle. What does that mean? It means I have to increase my sample size, right? Because the expected counts depend on the sample size. So the expected count is going back to the expected successes and failures, but now we have more categories, right? And it links way back to the sample size, right? So it's essentially asking, is my sample size large enough, right? So this is basically asking, is the sample size large enough? Maybe I'll bump this down. Right, that's technically what it's asking, right? But how we check it is you have to make sure that you have at least 5 expected counts in each cell, right? So even if we go back to last day and we had our expected counts that we found, right? First of all, right, you're going to be classified. So each of these counts are independent of each other because you're classified into one of these race categories, right? And so that assumption is checked. And then our expected counts, well, they were all well over 5. And so the assumptions have been checked, right? And so there's not a lot to it. It's just a different thing to have to consider. Okay, so good. So these conditions stay the same for any chi-squared test. Okay, so this is for any chi-squared test. Any chi-squared test. So that's nice because we're about to use another chi-squared test, right? Slight change. All right, so where's my page break here? Oh, not for a while. All right. No, I'll start it on a fresh page. Decisions. Started on a fresh page or no? So 6.4 is a chi-squared test for independence. Okay, so we said, okay, we've looked at one categorical variable. What if I have 2 categorical variables, right? And so let me just scroll there and just make sure that I've got the title of the section right. Yeah, testing for independence in 2-way tables. So long. Testing for independence in 2-way tables. So a 2-way table, let's start there. And this is a chi-squared test for independence. So let's start with a 2-way table. 2-way table just means that you have 2 categorical variables, right? Categorical variable 1 and categorical variable 2. Categorical variable 2, right? Each of them have some number of categories, right? And so we're going to have some number of rows, which we're going to denote by a capital R, and some number of columns, which we're going to denote by a capital C, which we've already seen, right? Because last example and last day, right, we only had the 1 categorical variable, and so we always just kind of show it spread across the categories because then it doesn't take up so much space is usually the reason. And it's just nicer to read, and there's all kinds of reasons, but so we've already seen this number of columns, but now we have the number of rows. I highlight that because we're going to need that for finding our degrees of freedom later. Okay, so let's see here. The idea stays the same, right? But now when we're testing for independence, we're saying, okay, are the counts across the categories in variable 1, are they independent of the categories that they're in for category 2? So notice how there's going to be some overlap here. Okay. And so we have our null hypothesis is going to be something along the lines of the counts in the categories or across the categories, let's say, across the categories of variable 1 are independent of the variable of the categories that they're in for category or variable 2 are independent of variable 2. I'm not going to talk about the categories so much, but they're in there, but it'll make more sense once we see an example. Okay. So we have to assume that they're independent before we can say that they are dependent on each other, right? What does that mean? It means that, okay, if you're in category 1 of variable 1, right, then you're more likely to be in maybe category 3 of variable 2. Right, that doesn't really mean anything right now. But before we can calculate a chi-squared, right, we need we have the observed counts in the table. So they'll be broken up in the table. And we've seen a two-way table before, right, way back in probability, right? And so we've seen a two-way table before. And so we know that there's going to be counts across each group, and we can find the totals, the marginal totals, the overall totals, right? And we're still going to use those. Okay, but like last day, we have these observed counts, and I want to compare them to the expected counts. So and of course, I'm not going to write the alternative hypothesis because it's just the counts in / across the categories of variable 1 are dependent, right, on variable 2 or some version of that. But just like last day, we will compare the observed counts with the expected counts, right? But first we need to figure out, how do I find the expected counts to find, because last day, right, we had some idea, right? We had some distribution that we wanted to compare our observed counts to. Now we don't really have that, right? We just want to know, hey, are these independent of each other or what? And so to find the expected counts, there's a little bit more work, not much, but the expected counts for each cell. Let me just grab it because they've got it written out so nicely. Here, way nicer than I ever could. Okay. So to find the expected count for the ith row and the jth column, right, we need to keep track of which little subcell we're in, right? We can find the expected count for row I and column j by taking, and this is where it gets a little bit weird until we see an example, then you're gonna be like, okay. We take the row I total, times the column J total, right? So we take those marginal totals of wherever we're at in the table and divide it by the table total. That's weird. Okay. Then once we have our expected counts, for each cell, we can calculate the chi-squared test statistic the same way that we did before. The same way we did before. Right? Chi-squared is the sum of the observed minus the expected. I'm just going to use O and E, which should be pretty self-explanatory, squared over the expected. And then I'll put square brackets around here just to emphasize that I'm summing all those. Right. I'm not using any subscripts or anything like that, but of course it's for each cell, and then we add them all up. Okay. Then to use the table, right, we need the degrees of freedom. So once we have the chi-squared, right, we need the degrees of freedom. The degrees of freedom for a two-way table is, or are, I guess. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So remember, R is the number of rows and C is the number of columns. So depending on how many rows and how many columns you have, right, you subtract 1 from each of them and then you multiply them together, right? And so maybe I'll just put a little X in there, right, to indicate that this is a multiplier, although I don't like X's because they're typically a variable in our calculation, and so it can get a little bit boggy. But here, I'll say multiply. All right, just to clarify. Okay. We have a chi-squared, we have our degrees of freedom, right? And now we're exactly back to where we were before, right? I can use the table and I can either find the critical value or I can find the p-value or a range of the p-value, right? So now we can use the table, the chi-squared table, to either find the critical value, right? So then it behaves the exact same way that it did before, and that's really nice. So find the critical value or find a range for the p-values. And then again, we use these to draw our conclusion, right? The conclusion stays the same. So if the critical value or if our test statistic is larger than the critical value, so the test statistic is our calculated value. Okay. And so if the test statistic, which is our calculated chi-squared, is larger than the critical value, which we've been denoting chi-squared critical, we have enough evidence to reject H0. We have enough evidence to reject H0. in favor of HA. But I'll just end it there because I've got a page break. Or you guys are more familiar with the p-value approach, so that's fine, right? If the p-value is less than the alpha level, but the more you work with this table, you're going to start to see that connection of, okay, either my test statistic is larger than some value, right? Or my p-value, which is the area in the tail, right, has to be smaller than some prescribed value. And so as we move out, right, the area in the tail gets smaller and smaller and smaller. So they're the same, right? They're just two ways of looking at the same problem. Okay, I wanted to do an example, this one. And I know, whoa, what happened? Okay, copy. I know it has the hypothesis, but that's okay. Okay. So we've got an experiment where we're evaluating treatments for type 2 diabetes in patients aged 10 to 17 who are being treated with metformin. So the 3 treatments considered were just the continued treatment of metformin, which we're denoting by MET, which is here in the table, right? And then the metformin combined with rosiglitazone, Rosie. I prefer that one. Or some sort of lifestyle intervention program. And so we've got lifestyle, we've got just continued metformin or metformin along with this rosiglitazone. Butchered it. Right, you can tell I didn't do pharmacology. So of course we have some primary outcome, right, which is going to be either they lacked that glycemic control, which would be a failure, right, a failure of this treatment, right, or they did not lack that control, which it would be considered a success, right? And so each patient in the lifestyle category, for example, there were a total of 234 patients in the lifestyle category. They're either going to be classified as a failure or a success, depending on, the outcome. So let's talk about the appropriate hypotheses for this test. Notice that this is a two-way table, and we've got the totals out here in the margins, right? The marginal totals. All right. So our hypotheses. Let's start there. Step 1, state the hypotheses. For a two-way table, it's always going to be a test of independence for us. There are other things that we could do, right? There are other chi-squared tests even, right? And so we're just going to focus on these 2. We could do a test for homogeneity, which is everything all the same in all these categories. Nothing's going on, right? Whereas for independence, we're saying, okay, well, does the category in the failure success categories, does that depend, right? That's really what we're interested in. Does that depend on the treatment that we gave it, right? But in order to determine that, we first have to assume what? We have to assume that they're independent, right? The outcome, so here, this is what we're going to call the outcome variable, right? Failure, success. So the primary outcome is what we'll call the name of that categorical variable, right? And then that's easier to talk about, right? And let's say here, this variable, we can call it the treatment variable, just so we can talk about variable 1 and variable 2, right? And so variable 1 is treatment. And here, variable 2 is primary outcome, right? Or just outcome. This depends on the question, right? So depends on the question what the variables are, but it's easier to talk about if you have some general name for each of the variables, right? And so what we're interested in here, so for our hypotheses, is the treatment, right? Or rather, let's talk about the outcome, right? Of course, we're most interested in the outcome. So is the primary outcome independent of the treatment that the patient receives? Right? And so is the primary outcome independent of, and that's going to be your key word here, independent, because we're doing a test for independence, right? So is the primary outcome independent of the treatment the patient received? Okay. Of course, it depends on the question, right? So I don't want to say variable 1 and variable 2 really, because I could have just as easily put the failure success in the rows and the lifestyle met and Rossi in the columns. So they're interchangeable. So you want to think about, okay, what's the main variable that I'm going to be wanting to talk about? Right, well, it's the primary outcome variable, right? So is the primary outcome variable or the primary outcome independent of the treatment? So our alternative hypothesis is that the primary outcome is dependent on the treatment, right? So the alternative is just kind of a switch. Or maybe I made this a question, but I shouldn't have. Let's just change that to the primary outcome is independent. Sorry, I don't know why I made that a question. Is independent of the treatment the patient received. Sorry, big cleanup there. I'm sorry. Give you some time to fix that. My bad. The question we want to answer is usually the null hypothesis as well, right? So it kind of makes sense, but I don't know. The null hypothesis, the primary outcome is independent of the treatment the patient received, whereas the alternative hypothesis is that the primary outcome is not independent. Sometimes we like to deal with negations, right? So independent or not independent, but you could say dependent, so / dependent of the treatment the patient received. Oops, I don't know how to spell received. That's okay. I'll just make it look a little bit weird and then it could go either way. Case in point. What does that mean, right? It means that okay, then the distribution among the failure and successes, right? The distribution shouldn't matter depending on what treatment you gave, right? Whereas what we're seeing here is we see quite a low count in comparison in the failure category for the Rossies versus the success. Notice that the totals are approximately the same, right? 234, 232, 233, that's roughly the same, right? And so, but now I'm kind of seeing this trend of, okay, there's slightly fewer failures in the Rossi category than I would expect to see if they were all the same, right? So if the distribution of failure to successes is the same, not necessarily even, but if they were consistent across the categories for the treatment, right, then that's what I'm testing. So our next step is going to be to calculate the expected counts. And once we have the expected counts, we can check to make sure that we have satisfied our conditions, right? Because we need to make sure that I have at least 5 successes, expected counts, sorry, in each category, or in each cell. So I'll call it step 2, do the test, which really means calculate the test statistic, which in this case is a chi-squared. But in order to do that, we need to find our expected counts. Okay. Need the expected counts first. Okay, so I'm going to bring this table down, copy, and I'm going to make it, trim it up a little bit, clean it up, and crop top here. Okay, these are my observed counts. I'm trying to stay on the same page here. So these are my observed counts. Whereas if I recreate this table, right, with the expected counts, I'm going to have some expected failures, some expected success, and I'm going to ignore the totals. The totals should add up to be the same, but because I'm kind of low on space here, I'm going to do it like this. So here I'll say life and Matt and Rosie. How do I find those expected counts? Well, what did we say? We said, all right, so this might be helpful to have somewhere along with your notes on chi-squared test for independence is, of course, you need to find the expected counts, which is the row total that I'm interested in times the column total over the table total. Okay, and so that's from the observed counts. So here, for this first cell, right, I have a row total of 234 times a column total of 319 divided by the grand total of 699. Okay. So here I have 234 times 319 divided by 699. 234 times 319 divided by 699 is roughly 106.79. Rounding, I got a bunch of decimal places, but I'll round, and that's probably good. For the successes, right, in the same row, I have 234. And I think I did 234. Let me just check before times 319. I'm just double checking the one I just did. Yeah, okay, good. For a second, I thought I did 243. Easy mistake to make. So you want to be really careful, right? So my row total is still 234, but now my column total is 380 divided by 699. So I would expect 234 times 380 divided by 699. 234 times 380 divided by 699. Roughly 127.21. Notice that if I add these up, right, they should add to the 234, 106.79 plus 127.91. Oh, sorry, 21. What was I thinking? 106.79 plus 127.21. 234. Phew. No wonder it didn't work out. All right. So then now that we kind of understand this, I'm not going to write out the calculations here, but I will write out the numbers that I get so that we can compare them, right? So 232 times 319 divided by 699, I get roughly 104.88. In theory, you could just take 232 minus 104.88, but you also want to just make sure that you're getting the same numbers, right? So you could check your work that way. And so 232 times 380 divided by 699 is 126.12. And finally, 233 times 319 divided by 699 is 106.33, and 233 times 380 divided by 699 is 126.67. Right. Sometimes I tweak my rounding to make sure that they add up, and let me just 104.88 plus 126.12 is indeed 231. So that's good. Whoa. 231. I need 232. The hexagons? I better check that again. Let me see. 106.33 plus 126.67. Yeah, that one adds to 233. Something happened in my MET one. 232 times 319 divided by 699. Ha. 105. That'll do, yeah. Good thing I didn't subtract and go from there, right? 232 times 380. I'm just going to confirm that one, divided by 699. 126.12. Okay, good. 105.88 plus 126.12. Phew. Now it adds to 232. So your totals should stay the same, right? Same thing if you do the column totals, right? 106.79 plus 105.88 plus 106.33. Let's see here, 106.79 plus 105.88 plus 106.33. Depending on my rounding decisions, right? We're a little bit flexible, but in here it does add to 319, so that's good. And I'm going to assume that it does the same thing, but I should check. 127.21 plus 126.12 plus 126.67 is indeed 380. So I'm good to go. That's just checking my work to make sure that the numbers that I have are good, right? You don't want to use these numbers that are off, right? So it's worthwhile kind of checking to make sure that the numbers are all working out before you do any big calculations. Because what's our next step? Now we can check conditions, right? And so maybe kind of step 0, which I'm inserting between step 2 and step 3, check the conditions. You could have just as well found these expected counts at the very beginning before you even stated your null and alternative hypotheses, right? And then you can check to make sure that you have at least 5 in each cell, which we do definitely. But here I just wanted to wait with the expected counts until we were ready to use them. And so the counts in each cell, right? They are independent of each other, right? There's no double counting or anything like that. And so the counts in each cell are independent. And all expected counts are greater than 5. So then we're good to go. All right, so then my chi-squared, my calculated chi-squared, which is what we're here for, right? Doing the test means calculate the test statistic, is the sum of the observed, minus the expected, then square it, divided by the expected. I'm going to write these out, but then I'm going to skip straight to the answer, right? So I do want to write out these summations, but then we'll go for the gold. So I'm going to be working as I read, so it doesn't really matter, or it really doesn't matter which way you go, as long as you match each of the cells observed and the expected counts. So sometimes I'll even jot down, right? Once you're more comfortable finding the expected counts, I'll maybe jot down the expected counts beside each of the observed counts, because then you just have them there, right? You don't need to make a separate table. Okay, it's just nice to see what's going on. Okay, so as long as you do each corresponding cell with the observed and the expected, it doesn't matter which order you do them. So I'm going to do them as I read, moving from left to right. And so I'm going to do 109 minus 106.79. I have to square that and then divide by 106.79 plus 125 minus 127.21, square that, divided by 127.21 plus 120 minus 105.88 squared. So this is tedious. It's not hard, right? Once you get the hang of it, it's not hard, but it is tedious. It's a lot of kind of work. But I like tedious things because it means I know what I'm doing for the next little while, and that's a nice feeling. And so plus, I'm gonna need 112 and 126.112 minus 126.12 squared divided by 126.12 plus 90 minus 106 minus 106.33 squared divided by 106.33 plus the last one, 143 minus 126.67. Oops, forgot one. It's a big deal. 143 minus 126.67. Squared divided by 126.67. Of course, at this point, you're probably thinking, I think I could do this in Excel or in R. You definitely can, right? But I want to show you just by hand so that you can just do it, right? You can do it by hand, but if you prefer to just do this calculation in Excel, that would be really easy, right? You'd have your observed column, your expected counts column, and then you can just write the formula that you want to do, right? The observed minus the expected, then square it, and then divide it by the expected, and then find the sum. It's fine. You can do that, right? So whichever way you prefer. I am going to cheat and find the answer, which turns out it is 8.16. Okay, so I have my chi-squared value. So step 3, so I have my test statistic. Step 3 is find the p-value, right? Or in this case, find the p-value. In this case, we can find or the critical value. We need to use the table, right? We need the degrees of freedom. So the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. In this case, I have 3 rows and I have 2 columns, right? We never count the totals. They're just there to help us find the expected counts, right? So it's the distribution of the variables that we're interested in. So I have 3 rows and 2 columns. So here we go. I have 3 minus 1 times 2 minus 1, which is 2 times 1, which is 2 degrees of freedom. I thought I was going to have more. You will, right? As soon as we get kind of into a 4x4 table, right? Then you would have 3 times 3. So then you have 9 degrees of freedom. So now you've got bigger degrees of freedom, but it really doesn't matter. The table stays the same, right? So now, right, I can focus on my table here. And with 2 degrees of freedom, I focus on the 2 degrees of freedom line. I can't stray from there. Everything else just falls away, right? And so I focus on the p-value, the upper tail area, and my 2 degrees of freedom. Okay. And so now what do? I take my calculated chi-squared and I compare it to either a critical value or I try to place it along this line. So a couple of things I could do, right, is if I take 8.16 and I try to place it along this line, notice they're all increasing. So 8.16 would be somewhere between here and here. So here, 8.16, and it's too nitty gritty to try to figure out which one it's closer to. The interval is all that we care about, right? So our p-value then, if we wanted to use the p-value approach, is somewhere between 0.01 and 0.02, right? Or let's say that we assume an alpha level of 0.05, right? Then our critical value would be 5.99. So notice how these are all the same, right? You can say, okay, if it's larger than 5.99, then I have enough evidence to reject H0, but that's because the p-value is less than 0.05, right? So here, let's say, assuming alpha is 0.05, the chi-squared critical is 5.99. Okay. Or the p-value is somewhere between, and notice how we have to read these from right to left, right? Because they're decreasing as we move out further into the tail. So the p-value is between 0.01 and 0.02. That's usually one of those decoy answers, right? Is when the interval is listed in the wrong direction, right? It's meant to make you pay attention to the order here because an interval can only go from smaller to larger. Okay. But regardless of how we want to approach this, right, whether I use the critical value or the p-value approach, I can still draw my conclusion either way, and they are going to be the same. So step 4 is our conclusion. And I'll start with the critical value approach. So the critical value approach, our conclusion would go like this, right? So since our calculated chi-squared is 8.16. So since our calculated chi-squared of 8.16 is larger than the critical value, of 5.99, we have enough evidence to reject H0. We have enough evidence to reject H0 in favor of HA. Or if we're doing the p-value approach, right? So you can use the critical value approach or the p-value approach. You do not have to do both, right? Just the one. So pick whichever one makes more sense to you. Yeah, and we'll have more opportunities to work on these two, right, in the next chapter. So it's not going to be a lost cause, right? Make sure that the connection between the two and that you're equally comfortable using either the p-value approach or the critical value approach. So, or using the p-value, since our p-value is between 0.01 and 0.02, 0.01 and 0.02, it is less than our assumed alpha level of 0.05. So it is less than our assumed alpha level of 0.05, which means that we have enough evidence to reject H0 in favor of HA. So of course, that's the same conclusion, which means we have enough evidence to reject H0 in favor of HA. Which our final conclusion, right, means that, okay, now I go back to my null and alternative hypotheses here. If I can reject H0, that they're independent in favor of HA, that they are dependent, right? That's my conclusion. The primary outcome is not independent / dependent, right, of the treatment or on the treatment the patient received, I guess, right? And so I can reword this slightly as long as I talk about the dependence. Therefore, the primary outcome is dependent. Oh, I'll start over, I can't spell. Is dependent. Dependent. Ugh, I give up. Is dependent on the treatment the patient received. Right. I know I'm all out of time, but that's it. You did it. So we've got two different types of chi-squared, and the only difference is you've got a one-way table, so then you test for goodness of fit, or a two-way table, then you test for independence between the two variables. Hey, nice job. All right, I'll post the chi-squared one assignment. It's just going to be a tiny one for practice, right? You've also got the textbook, but I'll post some practice problems before you do the quiz, but I didn't want to post them before we had covered today. Otherwise it would get confusing. All right. If you have any questions, let me know. Otherwise, have a great weekend. Good luck on your quiz, and I'll see you on Tuesday. Stop this.